Per quanto altro tempo.
Good to go? Okay, okay. So thank you for coming. So we have a double act today. So we have the pleasure of having Ario Altamura and Ario, who is the audience, both from the group, from the quantum theory group in Trieste, the University of Trieste, working with Angelo Bassi. They are both experts of various aspects of the system dynamics and the quantum to classical transition. So while Ario will cover, aspects of one formulation of collapse models, which is the gravity-induced one, which is the Schrödinger-Newton mechanism, Oliviero will address what?
Complementary test.
So thank you to both for talking and go on. Thank you.
So thank you. It is a great opportunity to discuss with you about this project I'm dealing with for so long, and because I had an hard time with this kind of equation, and it is good for me to have some feedback. So we put it on the archive last year, but we are still dealing with some problems about this model and the testability of this model. So I want to start with a brief presentation of the model, and so about this Schrödinger-Newton equation. And this model is treating gravity as classical and matter as quantum. So what does it mean? If you take the Einstein equation, you have on the left-hand side this quantity here, the curvature tensor and so on, and on the right side the stress energy tensor. So what you do is basically take the stress energy tensor as an operator on an operator in a Hilbert space, and then you have the state of your system, psi, and essentially you take the expectation value of this object. And this is for example, you have the density, the mass density of the system, and that's it. So in the end here is the source. It is sourcing the source of the gravitational field. And okay, but in the end you start from this equation, then you derive the Newtonian limit in the end, and you get a Poisson equation for the Newtonian potential V. Okay, this one below here. So in the end, what we are interested in is just this last equation. And okay, so then okay, no. So just to have an idea what this equation is, the main features of this equation, we take the simple case of just one particle, okay, and we see how it this gravitational potential enters the Schrödinger equation. So essentially, you have that this gravitational potential is sourced by the distribution, the probability distribution of the particle, and this distribution gives like a mass density. So after you solve the Poisson equation below, you put inside the result in the Schrödinger equation, and you get the Schrödinger-Newton equation, the equation at the bottom of this slide. So what does, as you can see here, for example, you have that this equation is nonlinear in the wave function. So for this can be like the main problem of the equation, because for example, every nonlinear equation, Schrödinger equation of this kind can produce some effects like superluminal signaling, so you can send information faster than light, and so on and so forth. In any case, this is an equation that you should intend only in the non-relativistic limit, and so okay, there is this problem, but is still an effective model, and so we are not going to talk extensively about this. but you should remember that this equation has some intrinsic problem because of the nonlinearity of the equation. And then you cannot even formulate this equation in terms of density matrices, because if it is nonlinear, then the equivalence of different ensembles is not valid anymore. So you can have two ensemble which gives the same density matrix, but when you do the evolution under this kind of equation, you will end up with different density matrices. So the main effect of this equation for one particle is the following. If you have some kind of superposition of two Gaussians, for example, one on the left, one on the right, in the end, this attractive potential, gravitational potential, gives you an attractive force between the branches of the superposition. This is the main feature of this model, let's say. So when you want to do an experiment, so you want to deal with some kind of composite object, okay, so a nanoparticle or whatever, you should take into consideration the equation for n particles. So you can see here you have the kinetic term, then you have this gravitational potential, and here you can see that you have some for J different with respect to K, you have some interaction between different particles. When J is equal to K, you have a self-interaction of the particle with itself. And then you have all these contribution, and you have to try to find some formulation for some equation for the center of mass wave function. So you are interested in general, in this case, in describing what happens to the center of mass of the system, and then you try to factorize the wave function in something like this. So you have some center of mass wave function and some relative some relative wave function with respect to the center of mass. And then you can rewrite the potential in this way, where this rho c is some mass distribution relative to the center of mass, and then you have the wave function of the center of mass squared, the modulus squared of the wave function of the center of mass. And this, yes. So I mean, I think. So you mean boson or fermions? I didn't think about this, but no, I didn't think about this, but maybe it's a good thing to look at. And maybe in the derivation they gave in this article, they consider this, but I don't know. So so this is the main reference I'm using in. Yeah. Yes, this one.
Yeah, I was wondering, like, whether put together Schrödinger.
Yeah.
Like, are there anything that leads to something like the cross?
Yes. 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 I mean, I think they are both some effective description of a more complicated, like microscopic theory. But yes, in the end, you should are the same kind of equation, I would say. Yes. But I think should be similar. Now I don't know exactly the Gross-Pitayevsky, and but should be a similar reasoning on. Okay. Okay. You have a smearing, yeah. Okay. So okay, and so at this point to have something an equation for the wave function of the center of mass, we have to do some approximation. So what was done previously in the literature is mainly these two kind of approximations. And so the first one is something like taking an average on the relative motion around the center of mass, so on this chi wave function that I defined before. And then you have to make some assumption on the localization of the wave function in the center of mass. So if it is well localized or not with respect to the object you are considering. So for example, if I have a sphere like this yellow sphere, no, and the wave function has this extension with respect to the system, you have some kind of good approximation to this equation. So when you do this, and so the variance of the center of mass is smaller than the extension of the object, you get this simple, let's say, simple equation for the wave function of the center of mass. And you can see here that this is this additional term. So you have some harmonic potential, okay, some kinetic term, and then this additional term coming from the gravitational potential. And here you see you have this resembles an additional harmonic potential acting on the wave function, and which is centered in the average position of the system. And then okay, there are also these terms, but we are not going to look at these terms because we are interested mainly in the derivation of the equation for the first and second moments of the distribution. So in this so okay. Yeah. Yes. So expectation value. Yeah. So it's nonlinear in the wave function. Yes. It's nonlinear. And okay, so I told you that one of the main approximation here is that we have to assume that the wave function has a variance which is small, but there are different regimes of the approximation. So one is the one I showed you before, and is just I have the wave function, the variance is smaller than the extension of the system, and then in this case, this omega Sn that I showed you here, okay, this frequency of this additional harmonic term depends on the density of the object, okay? While there is another possibility if you have that, so this object is made of atoms, and each
Sorry, can I ask you?
As a wave function, which has a variance. Here I'm writing it as the 0-point motion of the atoms. If you have that the variance of the center of mass wave function is smaller even than the wave function of the atoms of the system, you have another expression for this kind of frequency, no? And this will depend on the mass of the atoms of the object and on the 0-point motion here of the atoms of the system. And just to give an idea on what happens for a system made of iron atoms, you have something like this. So here, in this case, you have something that is more or less 10 to the minus 3 hertz. In the other case, you have an improvement of 2 orders of magnitudes. So in the end, it is important to look at the variance of the wave function because this tells you which kind of value you have to take between these two. and it will be important also later when choosing how to test the model and how to amplify the effect. So at this point, we can see we have to look for a signature of this equation, some way to see the effect of this term. And in the end, what is the idea in general is that this additional term is going to affect the variances of the position or of the momentum, but is not going to affect the mean position and
Sorry,
mean
do
momentum
you hear me?
of
Do you
the
hear me?
center of mass. And so,
Sorry.
for example, if you look at the uncertainty ellipse, you can see if the you have just the Schrödinger evolution, so you are killing this term, the uncertainty ellipse rotates in the phase space with the frequency omega and also rotates around itself with the same frequency. But when you add this additional term, this is going to rotate around the center of the phase space with the frequency omega and then rotate with a different frequency around its own center. Okay? And okay.
Do you hear me? Hi.
Okay. How can I?
Do you hear me?
I can write yes. I don't know.
Just state which is the question.
I can maybe. I try to.
Do you hear me?
Now? I know I cannot.
Hi.
But I cannot hear you. I don't know why. I don't know.
So,
maybe I can come in there.
Do you hear me?
Yeah.
Oh, okay. Hi. Sorry for the interruption, but first of all, I would like you to ask maybe a favor, if you can, just maybe when there are questions from the audience, we don't hear the person that are online do not hear the question very well. So maybe summarizing a bit to be helpful, if you can. And second, I would like to ask you, like, just to have an intuition about that. So essentially, you get like so you are the gravitational potential here, and then you like by going in the Newtonian limit, you get this Schrödinger equation here, and essentially this seems like a bunch of harmonic oscillator that are present if you write like that, for example, in second quantization or something like that. I mean, can you help me to have an intuition about that? So you have like gravitation that is an attractive potential, and then you get something which is an harmonic oscillator physics in this case.
What do you mean about harmonic oscillator, a bunch of harmonic oscillators?
I mean, you have like here, like in the right hand side.
Yeah.
Like, for example, you have p square over 2m plus 1/2 m omega square x square, which is like an harmonic oscillator, right?
But this is an external harmonic oscillator. I'm just adding like an harmonic oscillator, and then I'm considering the second term, which is the one arising from gravity.
Okay. I thought that this was also coming from gravitational effects.
No, okay. Maybe I can highlight this. So I'm considering a system in which I have already an external harmonic oscillator, and then this only the second term is the one coming from the gravitational interaction.
Okay, I see. Yeah. But also, I mean, also this second one is like an harmonic oscillator, right?
Yes, is similar to an harmonic oscillator. Yes, just the center is the the mean, the average of the position of the system.
So how should I see that? I mean, like we are starting from an interaction which is like kind of attractive, but it goes like 1/r, like the potential, the classical gravitational potential, and then you end up with something which is
Yeah, but in the end, in this case, what you have to think, or at least that's the way I think about this, is this harmonic potential is trying to give you a wave function which is less delocalized, no? So that is the attractive force that is giving you a localized wave function for the center of mass.
Oh, okay, I see. I see.
Okay.
Okay, thank you.
Okay. Okay, then what else? We have that in principle, from an experimental point of view, a lot of setups have this problem. So you have that the Schrödinger-Newton frequency is way smaller than the frequency. The only setup you can think about using torsion pendulum or something like that. For torsion pendulum, you can have a small frequency omega, but in general, this is not possible. Not yes, for a lot of experimental setup, you have higher frequencies for the harmonic oscillator part. So you want a way to like enhance the effect of this kind of potential. So it's not working anymore. Maybe. Okay. So at the end, what do you end up with? You end up with this equation for the means, for the mean position and mean momentum of the center of mass, and then you can see here the dependence on the frequency is only on omega, and while on the left you have this different value of the frequency, this omega q, which is essentially this object here. So you have omega squared plus omega Sn squared, and you take the root of this quantity. So as you can see, only the second moments of the distribution are affected by this gravitational potential, while the first moments are not. And then what is the idea is not like a brand new idea, but what we wanted to look is if we try to add a modulation to the frequency of the harmonic oscillator, we want to understand if we can enhance the effect of this gravitational potential, and make this in some way testable, no? So the idea is just okay. We take two frequencies, beta, omega, and omega, and then we jump between the two, and we have some parameters alpha that is going to be related to the switching time. So we have some time t1 and some time t2, which depend on alpha and beta, and then you have these two frequencies, omega and beta omega. So when you do this, you end up with a differential equation for the variances, okay, which has a coefficient matrix which is time periodic. So you have that after a period t, capital T, this is going to be the same. And if you have this kind of situation, you can use Floquet-Lyapunov theory to characterize the stability of the solution, and then this will be helpful while choosing the parameters alpha and beta to get an enhancement in the testability of this effect. So just to make an example, if you take the two cases. So one in which the Schrödinger-Newton effect is not present, and the other in which you have this gravitational potential, and you tune the parameter in the right way, you can have that the oscillations of the variances, for example, the variances, the position variance, is enhanced, while in the other case it stays like smaller. And then this is the main idea we want to use to enhance the effect. So now I just want to show you how the stability and instability region are. So here you see you have the two free parameters, alpha and beta, and depending on the choice of these parameters, you can end up in a region in which the oscillations of the variances is increasing exponentially, so this orange region, and otherwise you have another region, this blue region, which is a stable region. So the oscillations are bounded in time. And the idea is just that if you introduce another term, another harmonic potential term, okay, these regions are going to change. So if you are able to tune these alpha and beta in such a way, you end up in a situation in which in one of the two cases you are unstable, and in the other one you are in a stability region, you end up in a case in which you should expect two different behavior from the solution of the equation. Okay, and this I want just to remind that this is going to be valid, this stability and stability region, for the first moment, because they do not depend on the Schrödinger-Newton potential, and for the second moment without the gravitational potential, while these only for the second moment for the variances with the Newtonian potential. So this is still a toy model, so just parameters that to show that this makes sense. So if you do not introduce any modulation, you start with some squeeze state, and you evolve this in time, you see that the two cases, the one in which you have omega Sn equal to 0 and omega Sn different from 0, are going to be different, but the oscillation, the difference in the two variances is going to be like bounded in time, oscillate, and so on. While in the second case, okay, if you tune the parameters properly, you can show that this difference can be enhanced and can be exponentially increased in time. The problem can be also that if you have a variance which is too big, or you are exciting the system so much, you can also lose the system. So you have some levitated particle, whatever. You start this kind of protocol, and then at some point you lose the object, for example. So you should be like careful about the tuning of this parameter in any case. So the main problem is how you are going to model an open system for this kind of equation. So if you put this system into a buff, the problem is that you cannot use density matrix formalism, because the equation is nonlinear, and then you cannot in any case do this. So the only way, or at least that I know and that is known in literature, is just to take the Heisenberg equation, okay, for the closed system, and phenomenologically add some damping and some noise, okay? So now the problem is, how do you model this noise? And in general, what you can say, or in general, what everybody does is add some kind of classical noise, some white noise to the equation, compute all the quantities, and so on. The problem is that if you just add this term, this stochastic noise, white noise, classical white noise, you're going to be in trouble after some time. And I will show you why. And so you need to have some classical part and some part in this object. Yeah. Yeah.
If there are two such mass distribution particles,
Yeah.
how do you define the joint state or how do you define entanglement? That has to come somewhere in the open. So we are neglecting the other side.
Okay. So
if you have two such scenarios, two such particles.
Okay, two particles interacting with the.
How do you define it? And because they are no longer localized. The mass is distributed over space.
Yeah.
We have two such waves. How do we define entanglement from the center of mass?
No, wait. So.
Depends on which degree of freedom you are in.
But you mean it is this kind of potential entangling or not? That's no. No.
I represents the mass.
Yeah.
So it is no longer a localized part.
Yeah, you can.
So if I take two particles, usually entanglement is a pattern.
Yeah.
In this case, since I do not have a specific point where they are sitting, how do I talk about entanglement?
I'm trying to think about.
But there may be some place where there is possibility of one particle or possibility of other particle.
Yeah.
Okay. So
it depends on which freedom you are in.
the degree of freedom that is represented by the
You might have localized. Depends on which degree of freedom you're in. In any case, I mean, regions where you overlap, therefore you lose distinguishability between the two subsystems. So now, you have ways, Saro has ways to redefine. So there is a bit of research on how to redefine entanglement in where partial distinguishability. So you can come up with notions of entanglement.
In this case.
Sorry for stopping.
No, thank you, because. Okay. So, let's go on. And okay, so now we have to do some assumption about the behavior of this thermal noise. And one possibility, okay, that will be the one we are going to look at is we take this noise to be an operator, okay, acting on the environmental degrees of freedom and with these statistical properties, okay, which has mean 0 when averaged on the environment and has this kind of correlation function. So, which is related to the temperature of the environment. And when we are going to take the averages here, we are going to take the average on both the system and the environment. So we are in some way, since we cannot use a density matrix for the environment, we are assuming that the environment has some kind of state, pure state, and we are taking the average. Okay. The average on both the system together. And then if you do this and you compute from this equation, from the Heisenberg equation, you compute the equation for the variances, you end up with something like this. So you have some damping here. You still have this dependence on the frequency, the Schrödinger-Newton frequency in the coefficient matrix. And then you have some non-homogeneous term that has to do with the temperature of the system that is pumping energy into the system. And okay, then you can still use locally upon of theory because this can be extended to another case. The only constraint is that you need that the non-homogeneous term is going to be still a periodic function with the same periodicity as the coefficient matrix. And in the end here, this is a constant. There is no problem in doing this. Okay, then we can look at how the space, the parameter space is modifying. So the regions of stability and the instability are changed, but we can still find some instability region, and we can exploit this to amplify the effect that, as I showed you before. And in general, here we can still do it without going into an instability region. So we can take some parameters that are in the stability region for both the two cases. So with omega Sn equal to 0 and omega Sn different from 0. And then you can see that there is an enhancement even in this case. And we will show it also later. So now I just want to give another prescription to treat the environment and the noise coming from the environment. Another thing that has been done in the literature is the following. So you divide this noise into a classical part and a quantum part, and in the end what you do is you put your system interacting with a thermal buff with some temperature that is giving you this classical noise, and you at the same time this is interacting also with a buff with 0 temperature that is giving you this quantum term, this FQ here. And now in this case you have to define different objects, which are this sigma, okay? That is what you should obtain experimentally, okay? In which you have two kinds of means. One is a stochastic mean on the realization of the stochastic process, the classical stochastic process, and the second is the one on the state of the object of the system and this environment. So if you do the maths and you, okay, in this case you neglect this quantum correlation, you will end up this quantum noise. You will end up with this kind of equation that will depend on another quantity that is this V, okay, that you can compute without taking the stochastic averages, because without taking the stochastic averages, the classical noise gets cancelled, and you will end up with this kind of equation that do not depend on classical noise. I mean, this is, I think, really in some way strange, but this is what happens, and this is coming from the kind of prescription that they use for F, and also on the nonlinearity that is in the equation, in the Heisenberg equation. So the presence of the mean position. So these are the ingredients, and you need to compute both, because these sigmas here will depend on the V, and here you need the presence of this quantum term, because otherwise these two terms here would be 0, and we'll end up with a set of equation that does not make sense, because you will end up with a set of equation that gives you some kind of non-physical evolution for the variances, because you don't have anything that is pumping the system. You have just some damping, and we'll end up with something that is not satisfying, for example, the uncertainty principle and so on. So just to give an idea of what these two objects represents, in your experiment you have that on each run you
Sorry,
yeah.
I don't get it.
Yeah, this one.
No, just the comment that you made on something pumping. What do you mean? Because FQ term has zero average, right? So
the FQ term?
The FQ operator
has
zero average.
Yeah.
Right? So how is this guy pumping energy in the system?
Because as a zero average, but as not yes, because X and P will depend on this FQ. If you look at this equation here, okay. So at some point, the position and the momentum at some time depend on the FQ, and then in here you will get something like going back. You will get some FQ here, okay, if you solve the equation for X and P, and then the correlation function of this object is the following: is something like this is the correlation function for a buff at temperature 0, an ohmic buff at temperature 0, with some cutoff. So that's what is pumping this equation, let's say, is okay. And so okay, I was yes, in each realization of the experiment, you have a different let's say value for the different realization of the classical noise, and you end up with different different uncertainty ellipse, let's say. Each of these red ellipses is giving you the ending point of realization, and you see each of these as a variance, which is this V XX, this and then after you average on different realization, you get the state, what you would call the mixed state, which has this sigma XX variance. So the important bit is here that since omega Sn depends on the value of Vxx, you should be you should look at this kind of object, because as I told you, the approximation, the regime of approximation for the omega Sn will depend on this object, and you should compute what happens to these objects here. Okay, and then as I told you, the equation for the sigma depend on the V, and yes, you need the quantum noise to ensure physical evolution for the V. The correlation function for the F is this one, or at least is what has been done. And also the fact that you have this kind of non-white, you have a colored noise, let's say, you end up with some non-Markovian evolution for the V. And yes, in principle, you can try to use the protocol as before to amplify the value of this V, but if you amplify it too much, you're going to get a weaker value for the omega Sn, and is, I would say, really difficult to understand which is the sweet spot in this kind of story. So in the end, these are some experimental proposals that are present in the literature, but I'm not going to discuss it now because I don't think I have a lot of time left. How much time do I have? Okay. And okay, but just an idea what do this proposal look at is they consider some torsion pendulum. They have some cavity here to monitor the motion of the pendulum, and they look at the spectrum of these output fields, output modes of from the cavity. And okay, let's say what they expect is that in the spectrum they have two peaks, one centered in the frequency of the harmonic oscillator, the external harmonic oscillator, and another peak that is substantially in this omega q, which is the equal to omega squared plus omega Sn squared, and the square root of this quantity, you know. So in the end, if you have an high enough quality factor, you should be able to distinguish these two peaks, and so on and so forth. So they tried to do an experiment, but however, they couldn't find this signature of the model. but the problem was that they designed the experiment in a way that was wrong, let's say, because they expected some value for the frequency, the SN frequency, but in the end they discovered that the variance they had for the center of mass was bigger than what they were thinking of while designing the experiment. So this is not a conclusive proof that this is not that the Schrödinger-Newton is wrong, let's say, or is a wrong description of gravity. And okay, so at the end we try to we try to look at something like this. So we try to introduce some dependence of the harmonic frequency, and we try to look at the space of the parameters in order to find some parameters that will give an enhancement of the effect in order to test the model. And we were looking at magnetic levitation setup. So I just here some parameters we were considering with also Hendrik Ulbrich. And so you see here the frequency we consider is this one. We computed this frequency for the effect, and this is the external harmonic potential frequency. So at the end, what is the quantity we are looking at? In the end, this quantity is the relative difference of the position variance with or without the gravitational potential divided by the variance, the position variance without the gravitational potential. And this is the case without any modulation. So if you take a beta equal to 1, you have no modulation, and you see the difference, the relative difference is of the order of 10 to the minus 9, let's say. While if you start to play with the parameters and you choose some the parameters in a wise way, you can have this enhancement of the oscillations. And okay, here you cannot see the oscillations because the frequency is too high. But what we are looking at is the amplitude of these oscillations that I will call with this bar, okay, V bar. And okay, the final result is this. You have that you can get the difference between the two cases up to 10 to the minus 5, 10 to the minus 4, with respect to 10 to the minus 9. And here, this area here is taking into account the robustness of the protocol, because we were looking also at systematic errors in the setting of alpha and the beta parameters for the modulation of the potential. And okay, so this is the end. So the work is centered on a way to enhance the difference between the Schrödinger equation and the Schrödinger-Newton equation, and we also consider different description and prescription to deal with an open system. So when the object we are looking at is interacting with the buff, and maybe in the future we are going to explore, or maybe can be done to other effects in the dynamics. For example, introducing some continuous measurement on the object and so on. So that's it. If you have any questions, I'm here to answer.
Maybe it's time for one or two. Any question, comment from home or? Yeah. Okay. So that's the case. We thank you again.